there. So hi and welcome everyone to this fiber webinar once again. So we have a really interesting speaker today. We should soon be introduced. Just some things, you can ask questions to your speaker. You who are in Zoom, you can use the chat function or just raise your hand after and we will give the word to you. If you are following us on YouTube, you can use the chat function. We are keeping an eye on that. And any questions will be asked after the presentation. But it's time now to hear more about today's speakers. So I'll get an introduction. Or just, Annette, maybe you would just wanted to say something about the slide that we're seeing right now.
Yeah, I can absolutely do that. So we are arranging a conference in September, and we have a great speaker list here. So we really look forward to this conference. Still some spots left, so please you can register on the homepage, and and you will find it if you Google FibRe and Treesearch. And you can also then, when you register, it shows if you would like to have a poster presentation or an ordinary presentation, oral presentation. So I look forward to meet you all physically in Gothenburg in September. By that, I give the word to Eva.
Great. Thank you, Annette and Josephine. So today it's my great pleasure to welcome Caterina Czibula to give a webinar in the fiber spirit. So Caterina, you just told us that you came back from a research day in California. And when you're not in California, you're actually a postdoctoral researcher at Graz University of Technology. And before taking up that position, you conducted your PhD studies, both your master and your PhD at the Montan University Leoben, which belongs to the Austrian Universities of Technology, I believe.
Yes.
And we have, in fiber context, we have already, for those who have been attentive, we have already heard your name at least once, because a couple of months ago, we had a presentation by Professor Artem Kulashenko, who is a professor here at KTH, and you are actually a co-author on some of his research works. So now we are incredibly curious to learn more about your work in this area, which very much relates to characterization of all our beloved fibers. So Caterina, today you will be speaking on shining light on fibers, and we very much look forward to hear what you have to say today. The screen is yours.
Thank you very much for the kind introduction, Eva. It's my pleasure to be here, and yeah, that so many of you come along to listen to me after lunch. It's very nice. So you can lean back, and I'm going to tell you a little bit about Brien spectroscopy. So yes, as mentioned, I'm a postdoctoral researcher at the Institute of Bioproducts and Paper Technology at Graz University of Technology, and I have had a Firnberg position of the FWF, the Austrian Science Fund, with which I've been doing the last 3 years of my research. And today my goal is to show you and to introduce you to Brien spectroscopy. And I will give you then 2 examples. So first, it will be very general. I will try to tell you about this technique and then tell you how I'm applying it. So there will be 2 examples. One will be like the full approach, how we were able to determine the elastic stiffness tensor of cellulose fibers. This has not been done in literature yet. And then we will look a little bit into first results of hygromechanical characterization that I'm trying to do both with this method. Before I start out, I want to a little bit more give you a background about me. So I actually come from atomic force microscopy background. I've been doing AFM for more than 10 years now, so I've been always on the nanoscale, and only in my postdoc actually I started to work with all the classical mechanical testing techniques, tensile testing and whatever. And I was, wow, the first time I measured millinewton, it was wow for me, so high forces. And yeah, now further on in my project, I've started to go into high-speed testing, split Hopkinson testing, and then here the big focus is for me Brien spectroscopy. And yeah, I would consider myself a hardcore experimentalist because I'm now covering nano to macro scale, nanonewton to kilonewton, and millihertz to gigahertz, which is kind of cool. So I enjoy this a lot to work experimentally. Yes, and today I will focus on fibers, and I want to focus on two things. First, on the anisotropy. So we know that all these fibers, and this is just a scheme, a general scheme. I mean, it's not a very beautiful one, but we can take this general. That the fiber has a hierarchical structure and it has anisotropic properties. And when we now do tensile testing, for example, we will always be only able to get information on the axial direction of the fiber. You can do a little bit of nano indentation on the transverse side and then play around with methods, but it's very tedious and hard to get really with one mechanical method the full characterization of the anisotropy. And it's also experimentally tedious because it's very error prone. You really need to be on top to really make this very clean and smooth, and then it's very little data that you can get out of it. So this anisotropy has been kind of being on my way since the PhD studies. And another thing that has been always a bit of a focus is hygroscopicity. So I like this word a lot, but it's basically that the mechanical properties also change with moisture content in the fibers, and this is especially when you measure the fiber in water, you have a completely different material system at hand. And when you do it with contact-based methods, that, for example, indentation, you just go in there like it's like butter. So what we've been trying to do now in my postdoc time is to come up with a method to fully characterize the fibers in its anisotropy and to get now into better ways of testing all the moisture interactions. And so I started to work with this non-contact optical technique, Brilliant spectroscopy, and now I want to introduce you to it. So when you have a laser light and you shine it on a scattering medium, which is your sample, you will get scattered light. And there are different scattering mechanisms. There is Rayleigh, which is elastic scattering. It will stay at the same frequency as the incident laser light. And then there are two inelastic scattering mechanisms. One is very familiar, it's Raman scattering. Here the light interacts with the vibrational modes of molecules, or in other words, the light interacts with the optical phonons in the material. So you get the shifts very far off of the zero line of the frequency. And usually these peaks are pretty intense. It's a very local interaction, and you can get chemical information of your material. And there is a second inelastic scattering mechanism, and that is Brilliant light scattering. So here you interact with acoustic phonons. It's an inelastic scattering of light from acoustic phonons, which have a lower energy. And that's why it's not very local, but rather it's a collective interaction. So the light is directly interacting with the sound waves in the material. Basically you're propagating density waves. And here is the thing, you cannot measure with a Raman device Brilliant because due to this lower energy, these peaks are very tiny. It's not so strong here, but they are usually very small and very close to the Rayleigh line, and you cannot get that resolution with a Raman instrument. Here in the table, you see it a bit more clearly. Raman is really far off of the zero line, and Brilliant is very close. And the line width, so the width of the peaks is also much stronger in the Raman signal. Here's maybe a little bit to illustrate this to you. This is from a Brilliant spectrometer, just to make you see. You need to shadow out basically these elastic peaks to really see these tiny Brilliant peaks. You see now in the circle. I hope it's on the display. Should be visible, I think. These are the Brilliant peaks, for example. So they are very weak. And yeah, but now we want to use this method to measure mechanical properties. And how to do that? So we shine the incident light onto a sample in a specific geometry. And what we have in our material, we have thermal waves always propagating in all directions, basically. So they have a, and with the way I shine my light in and with the laser wavelength of my laser, I can determine the direction I want to, of the sound waves that I want to investigate. So the laser light is scattered from these moving sound waves in the material. And from that, this is recorded in the spectrometer, and then I get a spectrum. You have a very huge Rayleigh peak, which is at 0 frequency shift. So you always see the intensity now over the frequency shift, and the frequency shift in Brilliant is always in gigahertz. And then you can zoom in, and then you see your Brilliant doublet. So what we do now is you can do some smoothing of the data, and then do a Lorentzian fitting or DHO fitting to get the position of your peak. So this is the frequency shift, and this is roughly at 20 gigahertz. And you can also determine the line width of your peak. From the frequency shift now, you can determine via this formula the sound velocity in the material. And this is related via the refractive index of your material, the laser wavelength that you are using, and the scattering geometry, as I was mentioning. So the way you shine into the material and how you collect basically the scattered light from your material. You will see later that there are different scattering geometries that can be applied, and that changes this formula a little bit around. But basically, this is like the first main formula, and here already comes the second, which is relating the sound velocity to the stiffness in your material or your elastic constant if you have an anisotropic material. And this is only connected via the density of your material. So basically, when you investigate a specific material, if you know the refractive index and the density of the material, you have the full, you get everything from the measurement, because you know your geometry that you are using and your laser wavelength. And nice about this method is also that this frequency shift that we measure here, so these 20 gigahertz, they are directly related to the elastic properties of your material. There are no assumptions, so I don't say, okay, this is like in a tensile test, okay, this area is linear elastic, and then I do the fit there, or in nano indentation, where you have an indentation curve and then you have your contact model and assume certain things. We here, at least for this, it's like this is a direct relationship. Yes, so before we go now into examples, I want to show you a little bit with this simple sketch what you can expect from measurements. So I mentioned we are always getting the frequency shift and then also the line width of the peaks. And when we now take a biological material or a composite material, it doesn't really matter. And it consists of a reinforcement fiber, which is more solid, and the matrix around it, which is more viscous and gel-like. If you do measurements here, let's say we really make a spot just on the reinforcement fiber. I mean, this is like just an ideal illustration. In reality, this cannot be the case, I would say. But if you just measure this reinforcement fiber, which is a solid material, we will get usually a larger frequency shift. So the peak will be further away from the zero line, this large Rayleigh line, and the peak will be also very narrow. So the line width is small, and this is an indication of a stiffer material. So usually when the peaks are more narrow and further away from zero, the material is stiffer. In comparison, if you would just measure the matrix, you get much smaller frequency shifts. They move closer to zero, and the peaks are much broader. They have a larger line width. And nowadays, there are basically two setups which you can use to really get to these Brilliant peaks. And one has been the standard in in solid state physics and material science since the 70s. This has been developed by John Sandercock and is commercialized. It's a tandem multipass FibRe interferometer. It has a really high extinction ratio, so a very high resolution, and out of its application in its previous application, it's mostly used in point measurements. So you take one position and then you measure on that one, and it's not the same as if you would do a Raman measurement. It's taking much longer time depending on your material. The more translucent your material is, the easier it is to do the measurement. But yeah, for example, the fibers, they take a lot of time, and it also depends a lot on the scattering geometry that you are using. And the principle of this interferometer is that it consists of two mirror pairs. So this is here illustrated as one mirror pair. You have M1 and M2. And by the distance of these two mirrors, I can determine the frequency range that I want to measure. So I say, okay, I want to go from -30 to +30 gigahertz to cover so I cover 60 gigahertz. And yeah, I need so many millimeters of distance of the mirrors to achieve that. And the second thing is, one of these mirrors is always moving. So you have a piezo scanning, and with this movement of the mirror, you can scan that frequency range. So you will really go all the way from -60 to +60, -30 to +30. And then the signal is collected on a detector. In recent years, another spectrometer has developed. This is based on a so-called virtually imaged phased array, a VIPA, which is nothing else than a prisma with a higher resolution. So it's angular dispersive, and what it does, it has a certain frequency window. You shine your light into it, and then it will just immediately put the peaks onto the camera. So this is not scanning through the frequency. So it will cover a certain frequency range, and immediately image onto the camera. It has not as high resolution as the FibRe interferometer, but it's used more for scanning in scanning measurements, because it is applied a lot in the life sciences, because it's important to measure cells rather quickly. Otherwise, you get phototoxicity and all these effects, and that can be a harm. So it was especially developed for that, and that's also where it's nowadays mostly applied. I will only focus now in the remainder of the talk on the FibRe interferometer, because that's the instrument that I have been using, and I really like it. I enjoy doing measurements with this. It's really nice. Yes, and here maybe some applications in materials characterization that have been done with this sort of device. So there is, for example, this is what my supervisor in US is doing, Professor Koski. She's doing a lot of intercalation of 2D materials and looking on the elastic properties, how they are developing for when you put different intercalates into 2D materials. In the 70s already, there have been collagen fibers measured at different relative humidities. They went a little bit high with the laser powers. That is a little bit of an issue, but it's nice that you really saw also the development, that how the humidity affects the frequency shift of the collagen fibers. There is very nice work on bones, and it's also being here, Briand is used together with Raman spectroscopy to map the bone material. You can also apply it in really hardcore physics, so investigate spin waves with Briand, because for magnetic materials you can make the interaction of the light with magnets in your material. And I would say most it was applied to study elastic constants of geological materials, for example, also how they increase with pressure. So the study of anisotropy and determining the elastic stiffness tensor is pretty well established with Briand spectroscopy for mostly anorganic materials. I mean, there is also some on the biological stuff, spider silk, for example, and also on the collagen, it was applied. Yeah, but so far no work has been done on cellulosic materials or cellulosic fibers. So, and this is where I'm going to take you first. So I want to show you this how we determined the anisotropy or the full elastic stiffness tensor and really measured all the directions within the fiber. And I've been doing these measurements at the University of California, Davis in the group of Professor Koskisch. She is a collaboration partner in my Hertha Firnberg fellowship. And yeah, the last, since 2022, I've been visiting her lab always for a month and started to learn this technique. So the interferometer, this FibRe interferometer, I was showing you schematically, is hidden in this black box. And you can imagine, I mean, this was the first time I started to work with lasers. So a whole thing was a black box, really literally a black box to me. And yeah, you basically don't open this too much because that's never good. You want to keep it closed and in its own environment to not get any drifts or so. And you operate from outside. So you need to do some alignment to really do measurements, and there is some control that you need to do here. And the rest of what you see on this optical table is just how you get your light basically to the sample and away from the sample into the spectrometer. I mentioned you the distance between the mirrors is pretty important because it determines the frequency range that you are measuring. And I was at around 5 to 6 millimeters of mirror spacing. That's always between 20 and 30 gigahertz on each side. So. Yeah, and we mounted the samples here in the middle. You see it here, we're always measuring with green light at 532 nanometers. And what you see here, there are two objectives. And one is for the incoming and one for the outcoming. Sometimes you can do also the measurements that both the incoming and the outcoming light go through the same objective. And basically what I've did is I just mounted the fibers in. There was really, compared to any other of the mechanical techniques, there was nearly no sample preparation, which is absolutely lovely if you have ever worked with single fibers, especially wood fibers. I mean, it's just painful. So I just glued the fibers in and then turned them around in this holder. And what I've tried is that we keep the laser power below 5 milliwatts, because otherwise you would burn the fiber and that will also not have a good effect on your results. And what we could not control most of the time is the humidity in the room. So there is no humidity chamber. Yeah. And now I will guide you through this determination of the elastic stiffness tensor. So you see now I can mount the fiber horizontally and vertically, and I can go between that. So I was mostly started out horizontally, and then I turned it until 90 degrees, and in between always did some measurements. But basically we have all the freedom in this in this setup, so we can turn it all the way and also around itself. There are no limits there. And then we needed to assume a hexagonal model for the fiber. This is very common. Fiber materials are usually described by the hexagonal symmetry. And that's how this elastic stiffness tensor looks for such a symmetry. You have here the diagonal field with C11, C33, C44, and C66. And this diagonally, you can directly measure with Briand. So you get all the stiffness, ideally you get all the stiffness tensor components in the diagonal from the measurements. And then you just need to determine C12 and C13. We will come to that later. But first, I want to show you here So C11 and C33, they are basically longitudinal phonon modes, and you can determine them also with this second equation that I've showed you before. So here you just you use specific arrangements of the fiber. So when I have the fiber in this alignment in 90 degrees, I can measure my C11. When I have it in horizontally, I can measure my C33. For the transverse phonons, or like the shear modes in the stiffness tensor, so the C44 and the C66, I can measure the C44 in both alignments, but the C66 I would basically just get in the vertical, or else I need to leave the horizontal alignment, because due to symmetry they will overlap here. Yes, but it's maybe confusing to hear about longitudinal and transverse phonon modes, so we should go a little bit into that. I mean, in general, what is a phonon? A phonon is a collective excitation in a periodic and elastic arrangement of atoms, and we always have phonons moving around when we're above 0 Kelvin. And there are two kind of ways in which they move around. So in a solid material, you have always one longitudinal wave and then two transverse waves. That's in an isotropic material. As soon as we go into anisotropic material, you get quasi-modes. So these are kind of mixed modes. Then it's getting really messy. And I have to tell you, this is something still I also need to get into. This is very, very, very hard to comprehend. But yeah, so there are the transverse modes I would characterize by being Laola movements. So anytime you're in a stadium, you're doing transverse waves when you're in the crowd. And the longitudinal modes are basically in plane, this kind of compression and decompression. So this is what we are measuring, and there is a way also to distinguish between transverse and longitudinal. And that is very important, because if you don't know which one is which, then you will also not get your stiffness tensor components. And yeah, this can be done by using polarizers. So when I just do a measurement of this is a spectrum of a fiber material, you see the intensity again and the frequency shift. And when I measure this material with no polarizers in my light path, then I will get these two peaks. This is noise. This you can forget about. And on the other side, it always needs to be the same. So they should be identical. Otherwise, something is very weird with your system. Yeah, you get these two peaks, but you have zero idea which one is which. I mean, you can make assumptions from a theory, okay, but it's always good to check, because some materials act weirdly. So when I put in polarizers, which are oriented the same way, so here horizontal, I should be able to just see longitudinal phonon modes, and my transverse phonon modes should disappear. That's the case here. You see the larger peak is still visible, but this one is nicely distinguished. You have some background, but that is because fibers are just a heterogeneous mess. So here you can easily determine, okay, this is my longitudinal phonon mode. And then when you use the polarizers crossed, so you have the polarizer before the sample is in horizontal orientation, and when it goes through the sample before it goes to the spectrometer, it's in vertical direction. So here you should now just see your transverse phonon mode, and the longitudinal phonon mode should disappear. That's, as you can see, not as clearly as in the other case, but still that one is very nice. This is clearly a transverse mode, and here you have this kind of thing what I was mentioning. It's a quasi mode, you know, this is like a mixed thingy. Yeah, so we have now the elastic stiffness tensor. We turn our fibers around, and then we try to determine as much as we can in this diagonal. And we do that with two scattering geometries. So as I mentioned in the beginning, it's very important how you shine the light into your sample and how you get it from your sample to the spectrometer. And there are two main scattering geometries, at least what I have been using. And I would say the one in literature, which you will find most, is the 180A, especially in other life science applications. Now everybody will be writing about backscattering. And this is 180. So you can see it with 180A or R, and this just depends if you tilt your sample a little bit or not. But basically what you do here is you shine the light into your fiber. This is Ki, and you collect also into the same direction, that's Ks. And you will test your phonons. This is determined by Q in the radial direction of the fiber. So this is a reflective geometry. And then there is another one, it's 90A, and this is a transmissive geometry. Here I come with the incident light from one side, and I collect my scattered light on the other side. And this here we have a 90-degree angle, and the fiber is oriented at 45 degrees. And as you can see here, with this kind of scattering geometry, I can measure the axial direction of the fiber. That would be here only in 180. It would be only possible if I check cross sections of the fiber. So there would be again sample preparation necessary, and then whatever mess comes along with it. So this 90A is very nice to really get the axial direction without doing anything onto the fiber. And it's a transmissive mode. The disadvantage about this is you need to get your light through, and the fiber is not perfectly transparent. I would say it's the opposite. So as these kind of measurements take a very long time. Usually, I would say with 180, you can count for fibers, I would say about 30 minutes. And here there are measurements when you really also do this with the polarizers and then the cross polarizers, you have night measurements. So it will be going up to 12 hours at least. For wood, I made a record. So I went through a few cell walls just to check, and it took more than a day, 1.5 days, without any polarizers in it. This was initially when I started working with it, and then I thought, this really needs a lot of nerves, because if you mess up something, you will only see it very late, and then you have already lost a lot of time. Yeah. And now I want to go a little bit more into these scattering geometries that you get a better feeling, and I hope this is rather clear. So I really want to emphasize, so 180 is backscattering, so you always go in the same way as you go out, and you check the radial direction. And in 90A you can go axial as well, and you go through the sample and collect on the other side then. This is another illustration. This is how it actually looks in the setup. So we have the incoming light from this objective, and we also have the scattered light going through this objective down to the spectrometer. This is for the 90A, it's a top view. Here we have the incoming light here, and the scattering light goes here. This is 90 degrees, and the sample is oriented, as I mentioned, at 45 degrees. And now you can imagine if it's horizontally, it would be now lying in this plane. And as I turn in this geometry, the fiber at different angles, at 90 degrees, it would be looking right at you. Yes. And now some results of these scattering geometries and some further explanations about this. So initially I was starting out with 180 measurements because they are rather simple and it's rather easy to focus, because you here only need to control the beam in one direction basically. And I've obtained a few spectra on, this is, for example, these are several flux fibers, 6 or 7, and at some I even measured 2 positions. And as you can see, this is very repetitive even on natural fibers. So, and I mean, this kind of deviation is something you will rarely see in mechanical testing of single fibers. I was high-fiving myself because I couldn't believe. I mean, maybe you cannot share my enthusiasm about it, but yeah, if you've done tensile testing, it's just horrible. Also with the AFM, I mean, you just try to press down this deviation, but it's never really going down. So for me, this was super nice. But then reality hit, because there is one thing, when you want to go from this geometry to your sound velocity, you need the refractive index of the fiber. And that is, as I figured out, quite a mess. I mean, with the heterogeneity of the material, to really determine it nicely on the micro scale, it's I don't know, it's not feasible. I tried a few things. You can also do it with Brilliant. I just get huge scattering. So this is still work in progress. And when I consider all this scattering, and also the scattering that I have found is available in literature, we go again to about 70% deviation of the sound velocity, which is still nice if you compare to mechanical testing, for especially tensor testing. But yeah, it was a bit of a bummer. So that's why I have ultimately decided that 90A is the geometry that I should go with. I mean, also Christy has been very convinced about that. Yeah, but that was our learning process. And that's one reason for that is also, I mean, it has the drawback that it's very slow, but the nice thing is the refractive index falls out of the formula. So I just need to know my frequency shift and the laser wavelength to determine the sound velocity here. And so what we did now is, for this whole stiffness tensor determination, we stayed in 98 geometry, and we just turned the fiber in this setup and from 0 to 90. And from the 0-degree measurement, you can directly determine C33 and C44 and C66 are the same in this one. And at 90 degrees, at the axial, when the fiber is vertically aligned, you get C11, C44, and ideally C66 when you can distinguish them. And so that's the measurements that I did, 0, and then I went with a few points in between to 90 degrees. The few angles in between are needed because if you remember, we have the diagonal of the stiffness tensor, but we also have off-diagonal components. These are C12 and C13, and we need to determine them as well to really have the full stiffness tensor. So C12 is rather simple. You just need to, there is this, this is coming from symmetry, that C12 is actually related to C11 and C66. So that is a nice formula. The second one is not so nice, or the next three are not so nice. This is coming from the Christoffel equation. Yeah, what you, for C13, you kind of need to fit this formula. So this is actually, this is the, when you these formulas will give you the sound velocity of the longitudinal wave, the first transverse wave, and the second transverse wave at all angles of your of orientation. It's just very, very, very nice. And so you need a few data points for that. That's why I've been doing these other measurements. And as you can see here, the longitudinal and the first transverse wave are in a certain relationship to each other, because the formula is just different by this plus and minus. Yeah, and when you have done that, you can get your C13, and then you're basically complete. This sounds nicer actually as it is. To get here, it was a pretty tough road, and but when I show you, you will see that in the results. But when you have all, you might wonder, yeah, okay, elastic stiffness tensor, what then? And when you know all those C's, you can determine your mechanical parameters as you know it from testing, because they are all in relation to each other. And from that, you can get the Young's modulus in axial fiber direction, in radial fiber direction. You can get the bulk modulus, and you can get your Poisson's ratios. So for that, but you need really every C from the stiffness tensor to figure out and calculate these relations. And then ideally you can go and compare it to your classical mechanical testing that you have been doing. Now I will show you some results that we have obtained, and I will show you the results of two different fibers. First, I want to start out with a viscose fibers. So this is a very flat fiber. It is several micrometers thick, and it's rather broad. So it's very wide. And I took it because it's just cellulose, and we used it a lot previously in AFM studies to just check a few things, kind of a validation material or model system if you want. And as it turned out, it was pretty nice to measure, but there was one thing that was really weird. So we started out in the horizontal alignment of the fiber. So we would measure directly into the axial direction of the fiber. And when you look here, you see now the spectrums at all, the spectra at all the different orientations. And for the zero alignment, so this when the fiber is horizontal, I show you the two polarized spectra. When we have the polarizers in HH in and do the measurement, we should only get the longitudinal mode. And there is only one longitudinal mode that should be possible to see. And here already the weird thing started out, because as you can see here are two bumps. So there are really two peaks showing up. When we then put in the cross polarization, we got a third bump to it, which at least was possible to identify that must be a transverse mode, because it's not really visible here. So at least we got that. And then as we went along, we could see that this third peak here at 20 gigahertz, it would also give a very ridiculous sound velocity, which would not make sense. If you compare to literature of wood, it would be way too high. So, and this peak was barely moving. So when we went through all these orientations, we were puzzled that this peak would just stay here. And then we also compared this peak to the backscattering, so this 180 scattering geometry. And as you can see down here at 90 degrees, I only did the measurement there, that's why it's here. These two are overlapping. So the 90A measurement and the 180A measurement are overlapping, which means that actually what we measure here in the back is, if you wish, it's an artifact, or it is like it's just the backscattering signal also in this geometry. So you measure two geometries with one. This has been reported in literature, and it's kind of for glass fibers already. And this is kind of an indication that the material has very good optical waveguiding properties. But for me, it was very painful, because it would any evaluation we would do for the stiffness tensor would just not make sense, because yeah, that would not, it makes no sense that this stays like that. So once we figured that out, we could be clear that this is our longitudinal mode. And as you can see, it gets smaller with increasing angles. So the closer we get to the vertical alignment, so where we would just measure in radial direction of the fiber, the smaller it gets. And for the transverse direction, it was very difficult to resolve it, I must say, because the closer you get to the zero, and the more the orientation of the fire goes towards being vertical on 90 degrees, the higher scattering from the surface of the fiber is getting. So what you see here, these rough oscillation-like things, this is coming from the surface of the fiber, is coupling into the spectrometer, and you will not see any peaks there, because this is just like it's overlaying signal and noise, which is just very, very dominant on all the fibers, I must say. So as soon as you get to a vertical alignment of the fiber, this is very difficult to resolve peaks there anymore. Yeah, but we could determine at least the longitudinal peak and the transverse peak. And as it looked, there was no second transverse peak. They either overlap in this material, or it's not possible to dissolve them because they're so close together. You will see that now on the next slide. Yeah, and this is the backscattering signal that I was mentioning. So this is, I mean, in this case, for the determination of the stiffness tensor, it was an artifact for me. But I mean, it's another. It's still interesting to get this kind of new insights from such an optical measurement, because it's not just mechanics somehow. Yes, and when you do now this evaluation and plot these solutions of the Christoffel equation, as I've shown you before, you will get these curves over the fiber orientation. The points are the measurements that I have taken, and you see the longitudinal wave is fitted very well, and down here you see this is very close together. In frequency shifts, it would be very hard to distinguish that. I mean, transverse phonon modes are really, really tricky. And what you can see is we go from around 13 gigahertz with the longitudinal phonon mode down to 9 gigahertz. So the sound velocity is going from 5,000 meters per second to 3,500 meters per second when we have done 90-degree alignment or measured just the radial fiber direction. And now we can apply these formulas from before and get the Young's moduli in the axial and the radial direction, the shear modulus, because here, as I mentioned, we have only one transverse peak, so C44 is assumed to be C66, that the two of them are equal, and then the Poisson's ratio. Yeah, I must say, so you see the big deviation is in the Young's moduli actually. They are much higher in the Briand's measurements for the longitudinal direction. You see, I did some tensor testing on the same fibers. We get around 7 gigapascal. And also in the transverse directions, with AFM nano indentation, you would be around 4 to 5 gigapascal. The shear modulus are about a factor of 2 higher than what we got from torsion testing of wood pulp fibers. And the Poisson's ratios are really hard to tell because there are not so many measurements out there, or like mostly assumptions. But we did something on pulp fibers before, and we were kind of in that range. But yeah, but it's at least it's a full characterization. And yeah, before I go a bit more into the detail of this difference and what could be the reason for that, I will also show you shortly now the next results that they are more first results because they have been measured last month, so I'm not fully done with the evaluation. Yeah, this is on lyocell fibers. And actually, this lyocell fiber I just took out of a t-shirt. I bought a t-shirt with 100% lyocell fibers, and yeah, I was curious, and then I tested it. And again, you can see that the spectra at different orientations, they are changing and they're getting a little bit more scattery. This was the issue here. But we do not see this effect anymore of the scattering mode. So there is definitely a difference between these two fibers. That's also why I'm already showing you that. So that's not, you do not measure the same thing with each fiber. So you can distinguish differences. And yeah, we found here one longitudinal mode and again a transverse mode. And when we try to do the evaluation with the assumption that also here C44 is C66, it did not work out. So here we actually get that there should be a second phonon mode. And again, what you see is that the longitudinal mode is really nicely fit. So here the sound velocity is really a good fit. And I should also mention in these plots, I mean, I think they are very unfamiliar, but yeah, it's very hard to describe them. But what you should consider in these formulas, what I was mentioning, this plus and minus, this difference, there is a certain relation. So you cannot just randomly fit in there. It will give you a really ridiculous result, or it will not be a stable crystal structure. So this is not random what we are doing here. We are right now just trying and grasping what is happening and figuring things out. But I have to say that the fitting of the longitudinal modes is really working out well. So this is, I would say here there is a lot of confidence already that I'm having. The phonon modes are the ones that are tricky. They are really, really hard to figure out, and there is still a lot of work in progress there. Yes. And again, here we also did this evaluation with the mechanical parameters, and the trend is the same as for the viscose. So here we have much higher Young's moduli from these measurements than we get from tensile testing of lyocell fibers. And this is just the tensile tests, so just the literature value. I have not actually done evaluated the tests yet from this sort of fiber, and also cross sections I have not looked yet at, but they should be spherical, I guess. Yes, yeah, and the reason why this could be such a difference is, I mean, I think there are maybe two explanations that we have now, and I think they are pretty similar. I mean, you can look at it from a viscoelastic point of view. So if you consider your fiber as viscoelastic, and we used to describe that a lot with these spring dashboard models. So the elastic part is described by the spring, and the viscous part described by the dashboard. And now you apply a slow force. All your elements have time to react, also your dashboard. But if you now go into a high frequency regime, as in Brio, I mean, we measure in the gigahertz, this dashboard is likely to not have enough time to react. So everything will be just depending on the springs. So you kind of cancel or inhibit your viscous deformation. And the same thing is also coming, if you look at it, these viscose fibers and also the lyocell fiber have a certain degree of amorphous disordered structure in themselves. I mean, especially the viscose fibers, I would say. And actually, a review of my paper came up with this comment, so I really liked it. This was like very, very constructive, and I did not know about it at all. There is this non-affine theory for disordered solids. So, and when you deform a crystal, you will always have your atoms in the material will be always displaced proportional to the global strain that is applied to the material. But in an amorphous solid, as you can see down here, this is not so much the case. So actually, if you deform the material, you see here these dashed lines, that's where they actually should be, but they relax to that positions, and that's kind of called non-affine displacement. And when I test at a very low frequency, of course, the atoms have more time, and then they go to this they have this or have more of this non-affine movement in there. But when I test very quickly, this is kind of inhibited. So it's kind of the same. I would say it's a materials perspective and also a mechanical perspective, which is kind of a possible explanation, but this needs also much further look into. So there is not much literature out there which really compares mechanical testing to Brio testing. Just in the life sciences, they focus a lot of the comparison between AFM and Brio, but that is another story. So I've finished with that, and now I'm seeing that I'm really slowly. So I will quickly go also into hygroscopic measurements. Sorry, that was taking longer than I expected. I go quickly through that because they are just first results, but I've been also trying to check different humidities. And as you can see here, there is an effect. So we can go from 40% humidity, we went to 75% humidity, and what we see is that the peaks are clearly going to a lower frequency shift position, and they also get broader. This is also possible in 90A, although here the measurements, as they take longer, the resolution is not so good. But you can take also here these results and get the stiffness out of it. And as you can see, it basically goes, it drops to half the value when I do this for 90A now. And also the sound velocity is decreasing by around 1,000 meters per second. And now what you can do, and this is like only first results and a little bit of checking, you can take the peak, the stiffness of the 40% humidity, the 75% humidity, and then you can also determine the peak width that you have in water and make kind of this use of mixtures. And then it's a similar trend as we've seen now. When we then estimate that just the cellulose in that case, or this microfibrillated cellulose that I was testing here, we can go up to, it goes up to 27 gigapascal, which is again pretty high, but yeah, it must be really a thing about the frequency. And I mean, you also would not expect water to have 2 gigapascal, right? This is as if you dip it into water or jump into water from a high spot. Yeah, with that, I'm actually at the end. I'm sorry it took a bit longer, and I hope I could give you a nice introduction. It is very difficult to explain because there is so much behind it, and I was really trying to get it all. Yeah, and you can see there is a lot of possibilities. There has not been so much done on the cellulose materials. I mean, we've just started with that now, and it's very challenging. And as an outlook, I would be very interested to continue with anisotropy and now slowly introduce hygo and thermal measurements and also time resolution. The question is how to relate with mechanical testing. And that's maybe a bit of a teaser. So it's also working that to really do time resolved measurements. We could do that we can look at drying at least of cellulose material over time. And we've had 2 minutes change in between. Yeah, with that, I would like to thank all the collaborators, especially Christy, for letting me work in her office and being just an extremely brilliant experimentalist. She's really role model for me. And also my supervisor, Ulrich, and Manfred Ulz, he's helping me a lot with the mechanics. He's my guiding light here. I want to like to thank funding and you for your attention. Thank you so much.
Thank you very much, Caterina, for shining light on us this
Yeah,
afternoon.
I hope it was okay. I see that it was a bit longer. Sorry.
Let's open up. It was a brilliant and beautiful presentation, Caterina. So let's open up for questions. Josephine, have you seen if there are any questions in any of the channels that we're employing?
No questions so far.
No questions so far. So why don't I start? Annette, were you about to say something or?
No, go ahead.
No,
I have a question later.
So indeed, it seems to be a very complicated, I'm a synthetic chemist, so maybe I express myself badly here, but it seems to be a quite complex mechanism behind the characterization. So do you envision that it's sufficient to measure one sample, or would you have to measure on several samples to actually get, because you were observing these big differences between tensile testing and the results that you got. Do you think that can be addressed by measuring several samples to accommodate for variations?
No, I think this is you will not change this difference anymore between tensile testing and Brion. It will be always there. I think this is really coming from the basically it's coming from the frequency difference. You're in hertz when you do tensile testing, and you are in gigahertz. So it's like really you really only test also the elastic properties in there. And I've done repetitive tests also of some of the orientations, and I think with the Brion you would not need to go through a lot of samples to really narrow down the stiffness test. So this is maybe really nice. So I've been doing a few fibers in the same orientation, and I see there is the same trend. Maybe a little bit. It's always, but it's really making me very confident in that at least.
So that's a really nice advantage then. That yeah, absolutely.
Exactly, yeah.
So now we have, yeah, please.
Yeah, and maybe this can be then also used, I mean, it needs to be, more stuff needs to be measured actually to really figure things out.
Thank you. So now we have two questions from Åsa. So why, Åsa, I will ask you to raise your questions yourself. Åsa, I think you can talk now.
Hello, can you hear me?
Hi.
Yes.
Hi, yes.
Hi. Oh, I didn't know this was possible.
Magic.
That's nice. Thank you for your talk. It was very interesting. So I work with nanocellulose paper, so I was curious about what's been done on like CNF papers with this technique, and also could it be used to kind of probe the difference in mechanical properties like in plane of the paper and out of plane of the paper? Is that possible?
Yes, definitely. That is for sure possible. You just need to change the orientation. I mean, I've been doing that now with the fiber, basically. You just go around. But I would assume your paper is mostly isotropic, so I would not. It should be then the shift should be the same.
Yeah,
If you
I wondered, like, it should be different maybe in the plane of the paper, like kind of between the layers of the paper.
Okay, that could be, yeah, but I think that is accessible. I mean, there have been no measurements done on cellulosic materials except what we have been doing. There is so that the fibers that I've shown you now, this is like first results. Nobody else is doing this method. It's mostly in the life sciences now. But you sent me samples, right? So I've
Yes.
done some measurements for you, but I'm
Oh,
not
nice.
I'm not gonna spoiler now.
No. Okay, it was a leading question.
Yeah, there are some
But nice.
differences. I can tell you as much.
Ooh, okay,
But
very excited to
we
hear
would
more.
need I would need some more details on the material for the evaluation then. But we can
Yeah.
discuss this extra.
Sure, let's discuss that another
Excellent.
time. Thanks.
Excellent. So in the interest of time, Annette, you already sort of alluded to that you have a question coming up.
Thank you a lot for the very nice presentation. It really gave a lot of new insights. But if you go back to slide number 29, I just had a curiosity-based question, and that was here. You have the stiffness and you have different relative humidities, but and you plot them in a linear shape. Is this? I mean, the water uptake in the fibers will be very dramatic different. Do you think that?
Yeah, it was a very bold move of mine. So I went with this very bold assumption because I just thought, like, I mean, there is not much, I'm just trying.
Yeah.
And then I measured this 40% humidity and the 75%, and I thought, putting a fit for that is kind of weird. But we know so little about 100% humidity and actually how close that is really to water. I was like thinking, I just give it a try, and then I just took, because anyway we are in the gigahertz, and this value is 2 gigapascal for water. I mean, can you imagine that? It's weird for the mind, and then I just put the line through, and I mean, in comparison to all the other measurements, it's actually not so unreasonable. It should just demonstrate you. I mean, this is not now something that I would go, and it's just first results, but I would like to, kind of cover maybe different relative humidity and just see where it takes. And this is very often done. Do you use of mixtures?
I was thinking that the water maybe have not a non-linear influence on the stiffness. So if you take up more water, maybe I don't know how that will change.
I know from the AFM measurements that I did in the here it is, in the transverse direction, so radial of the fiber. I did actually a lot of humidities and then also measurements in water. And we see when we are changing the relative humidity, we have a linear decrease of the elastic modulus, let's say, and then in water we have a drop. So we go here from around 1 gigapascal to 50 megapascal. So this is really a pronounced drop and in water the fiber is completely different. But actually filling out these blanks here, this is really hard with any experimental technique, I would say.
But I really liked your presentation, and I can see so much potential in it. So thank you a lot.
Thank you very much. That's kind.
So I also would like to thank you, Caterina, on behalf of the entire Fiber for, again, shining light on us this afternoon and introducing us to this very exciting world. So with that, I'd like to close this webinar and thank you, all of you, for attending this webinar. Thank you so much.
Thank you.
Thank you. Bye.
Thank you.
Bye.
Goodbye. Thank you.
We will be in touch, Caterina.
Okay, great. Thank you. Goodbye.
Bye-bye.